So thanks everyone for coming along today. Today we've got a webinar by Ethan Coffel. Ethan is an assistant professor at the Department of Geography and the Environment at Syracuse University in New York State. His research quantifies the impacts of climate change on people and the natural ecosystems they depend on, and works to better understand the physical mechanisms leading to the intensification of impactful weather and climate events in a warming world. His recent research has focused on heat stress and the impacts of temperature on agriculture and infrastructure. And I'll throw over to you, Ethan, to start whenever you're ready.
All right, thanks, Cass. And yeah, thanks for inviting me, and thanks everyone for coming. So I'm going to tell you about some ongoing work, thinking about sort of the distinctions between dry and humid heat and how they're changing. So this is all still somewhat preliminary, so I'm interested in people's feedback and questions at the end. Okay, so to start off with, part of the motivation for this was this interesting fact that it seems that models are generally too humid over land. And so this is a recent paper from fall of 2023, where the authors show that basically over a lot of global land, models overestimate specific humidity. And they proposed a few reasons why models may do this, but ultimately it's not completely clear what the physical cause is for the overestimation of humidity across the CMIP6 model suite. But of course, if it is the case that models are overestimating humidity, this is important for thinking about heat stress. And so this kind of got me thinking about model representation of humidity and sort of how the coupling between temperature and humidity may be changing. So just to start off with, probably people here know what the wet bulb temperature is, but just to review it, this is the
Ethan, we don't see your slides anymore. I don't know if that was intentional or not.
Oh, I can still see them fine.
Oh, maybe it was just me then.
Can everyone else see them? Let's see. I'll reshare.
Well, Laura says she can see.
Maybe it's just me then. That's funny. Yeah, now I see the wet bulb slide.
Got it. Okay, sounds good.
Okay, if anyone else doesn't see his slides at some point, just drop a note in the chat.
Yeah. Okay, yeah, so wet bulb temperature, right? Temperature of adiabatic saturation. It's another way of stating it is the lowest temperature that you can reach through evaporative cooling. And so the wet bulb temperature is relevant for heat stress, right? Because at least in theory, if the wet bulb temperature exceeds the human skin temperature, you can't lose heat through evaporative cooling. And so this is thought to be sort of a physical limit to the human heat tolerance. Of course, heat illness occurs well before the wet bulb temperature reaches the human skin temperature. But this is sort of the upper limit. And so that limit is thought to be around 35 degrees Celsius. If the wet bulb temperature exceeds that, people will be unable to control their body temperature. Historically, that wet bulb temperature threshold has not been reached, but lots of research suggests that it will be approached and potentially exceeded in some places as the world warms up. There have been some instances of this threshold being reached, but it's not particularly widespread in the historical climate. So this is the wet bulb temperature. What we're going to be talking about here is a metric, the correlation between the daily maximum temperature, which is Tx, and the daily maximum wet bulb temperature, which we're going to denote Tw. And so if this correlation is higher, it suggests that temperature and humidity tend to co-occur. And if this correlation is lower, it suggests that temperature and or like high temperature and high humidity tend to occur at different times. And so if we just look at some historical data, what this is showing is we take the warm season at every location. So here the warm season is defined as all the months in which the maximum temperature or the maximum wet bulb temperature have ever occurred. So it's just in the mid latitudes, right? This is mostly July and August. In the northern hemisphere, mid latitudes, and in the tropics, it's more complicated. Depends where you are, but it's just all the months when the hottest temperature of the year has occurred. So we take the local warm season, then we take the daily TX values and the daily TW values during that warm season. We detrend them and calculate this correlation. And that correlation is what is shown here. So this data is from ERA 5, and this spans 1981 to 2021. So generally, the patterns we see, right, are that in the basically everywhere outside of the tropics, these correlations are strongly positive. So across North America, across Europe, and across sort of the southern hemisphere mid latitudes, these correlations are, say, 0.5 to 1, indicating that hot days are usually humid. And this makes sense, right? So generally we don't have the dry seasons in the mid latitude regions, and so when it's warm, it also tends to be fairly moist. So in the tropics, though, things are different. There's a lot of places where these correlations are negative, and basically this indicates that part of the year is hot and part of the year is wet. And if you have a negative correlation between temperature and wet bulb temperature, it's indicating really that the hottest days of the year are occurring at different times from the days of the year with the highest wet bulb temperatures. Okay, so this is sort of the historical picture. Now we want to think about how this is changing. So if we go back to 1980 and look at trends in the annual mean, the annual and global mean TX-TW correlation, we see a strong downtrend. Averaged across the whole world, this correlation has been declining. And so this indicates that in general, temperature and wet bulb temperature have been becoming more distinct. So if we just think about sort of the top level reason why this is occurring, on the right-hand side here, on the x-axis, we have the global mean correlation between TX and specific humidity. We calculate the global mean detrended anomaly in this TX and specific humidity correlation. And then on the y-axis, we have the global mean correlation between TX and TW, like again, the detrended anomaly. So if we plot these things next to each other, they're strongly related with this R squared of 0.59. And so this indicates that years with more negative TX humidity correlations also have more negative TX-TW correlations. So this makes sense, right? This is really driven by changes in the correlation between temperature and humidity. And in a lot of the world, in general, the correlation between temperature and humidity is going down. Okay, so if we just look at spatial trends or spatial patterns in the trend between the TX-TW correlation, they look like this. So this again is 1981 to 2021. Brown colors are showing places where the TX-TW correlation is declining. Green is the opposite. So if we just look sort of in sort of latitude bands, we see general declines basically everywhere, but the strongest declines sort of in the northern hemisphere mid-latitudes, and then also in the southern hemisphere subtropics. And these places with these big declines that really stand out are parts of South America, so sort of the south and eastern parts of the Amazon, a lot of southern Africa, particularly this region in Central Africa, and then parts of Mexico and the southern United States as well. Other regions too, but these are some of the ones that stand out. And then there's sort of just a couple regions of the world where there are increasing trends in this TX-TW correlation, one in northern South America and another in South and Southeast Asia. So these are sort of the ways that that TX-TW is changing. And now we want to think about what are the drivers of this. So just sort of by definition, if TX-TW correlation is declining, it either means that humid days are getting relatively less hot or hot days are getting relatively less humid. Not that the days are sort of in absolute terms getting cooler, but that sort of relative to other days, humid days are getting less hot, or relative to other days, hot days are getting less humid. And so we're going to think about this with two metrics. The first is the TX value on the day of the year with the highest wet bulb temperature. So we're going to denote this with this, this notation, TX on TWW, with TWW being the highest wet bulb temperature of the year. So this is the temperature on that high wet bulb temperature day. And on the other hand, the wet bulb temperature on the hottest day of the year. So these are sort of giving us a sense of, if we think about changes in these two metrics, they're giving us a sense of how sort of how that coupling between temperature and humidity is changing on the sort of extreme days of the year. So first of all, if we're thinking about this metric TX on TWW, so the temperature on the highest wet bulb temperature day of the year, if we plot trends, first of all, in TX-TW correlation on the x-axis against trends in this metric, TX on TWW, on the y-axis, every point here is a global grid cell. And what we see is basically not much of a relationship. So places where the TX-TW correlation is going down don't really have a strong sort of correlation with trends in the TX on TWW metric. So R squared value is really low, so these things are not super related. On the other hand, though, if we look at TW on TXX, the correlation is much stronger. So R squared here is about 0.3. So places where the TX-TW correlation is more negative have more negative trends in TW on TXX. So this is saying that in these places where the TX-TW correlation is going down, the hottest day of the year is getting relatively less humid, and the wet bulb temperature on that hottest day of the year is either going down or increasing less. So this is really what's driving it. It's that the hot days of the year are getting drier. Okay, so just to look at this in another way, we're going to look at some moisture variables and their relationship between the TX, the relationship with the TX and TW trend. So what we have here is on the x-axis, we've taken all the global grid cells and calculated, sort of grouped them into deciles of their TX-TW trend. So this is saying all global grid cells with the TX-TW trend in the 10th percentile of the full global distribution are grouped, and then all of the grid cells closest to the 20th percentile, and so on. So we've got basically just the distribution of TX-TW trends on the x-axis. And on the y-axis, we have the distribution of trends in 4 moisture variables. So in green, precipitation, brown, soil moisture, blue, evapotranspiration, and red, specific humidity. So we're looking at how do the trends in these moisture variables vary with the trend in TX-TW correlation. And this is, so we're looking at trends in the moisture variables during the part of the year when the maximum TX occurs. So the part of the year that tends to be the hottest. And so probably like we would expect here, what we find is that places where the TX-TW trend is lower, so either less positive or more negative, these places have lower trends in their moisture variables, indicating that the region is getting drier, right? So if we just look at specific humidity, so the red circles, these show a pretty strong relationship with the TX-TW trend, where the low deciles of the TX-TW trend also have the low deciles of the specific humidity trend. And so we're showing consistency, right, between these humidity trends and these other moisture trends, suggesting that these places where the correlation between TX and TW is going down are generally getting drier in terms of precipitation, soil moisture, ET, and then of course specific humidity, which is really the key link between TX and TW. Okay, so we've shown here that declines in the TXTW correlation are really occurring because the hot days of the year are getting relatively drier. The next question we want to ask is how models represent TXTW correlation and whether they capture the decline that we've seen. So this is sort of the CMIP6 historical change in the global mean TXTW correlation and its projection going forward. So the black line is the mean across 13 CMIP6 models. So I took all the models with daily data for daily data that allows me to calculate wet bulb temperature. So that's the black line. The red line is ERA 5, and the gray shaded region is one standard deviation across the CMIP6 model suite. So the vertical dashed line represents the division between the CMIP6 historical run and the future run. So for the future run, I use SSB 245 here, which is sort of a mid-range scenario, ends up with maybe 2 to 2.5 degrees of warming by the end of the century. So on the y-axis, we have this global mean TXTW correlation. And in general, ERA 5 and CMIP6 match pretty well on this figure, right? So they have approximately the same values of the correlation, and they both show a declining trend. But if we look a little more closely, we start to see some differences. And what we have here is on the y-axis, we have trends in the TXTW correlation. I mean, these are trends per decade between 1981 and 2021. And we're showing 3 data sets here. So on the left box plot is LENS, which is the large ensemble from CESM. So there's 40 members in LENS. The right box plot is CMIP6 across those 13 models that we have available. And then the red line down at the bottom is the ERA 5 trend in the TXTW correlation. So what we see, first of all, is that the trends in this correlation between CMIP6 and LENS are approximately the same. But the trend from ERA 5 is way below all of the model trends. It's outside of the range of internal variability represented by LENS, and it's outside of the range of cross-model variability represented by the CMIP6 suite. So it seems like the TXTW correlation is declining quite a bit more in the ERA 5 observation-based data than it is in climate models. So these trends are per decade. So you might ask, well, perhaps the models have been warming at a different rate than the real world. And that is true. And so if we convert these trends into changes in the TXTW correlation per degree Celsius, again, across 1981 to 2021, we get a slightly different result, but not dramatically different. It looks like this. So again, the blue and green lines represent the means in LENS and CMIP6. So those model means are approximately the same at about minus 0.3 per degree C. And then ERA 5 is, again, substantially lower, closer to minus 0.4 per degree C. So one thing that is interesting to note here is that the variation between LENS and CMIP6 is very similar in magnitude, suggesting that basically internal variability drives a lot of variation in this trend in the TXTW correlation. And internal variability really accounts for most of the variability across the CMIP6 model suite. So it's not really that CMIP6 models are behaving that differently. It seems like most of this variation across those models can be accounted for by internal variability. And the ERA 5 trends are still below that range of internal variability, though there are a couple models in LENS that, or a couple ensemble runs from LENS that do sort of match the ERA 5 trend in TXTW per degree C, but most of the ensemble members have a weaker trend than is seen in ERA 5. Okay, so we have said that the real world trend in this TXTW correlation seems to be lower or more negative than is represented in models. And so what we're going to try to do now is make an adjustment to the models to sort of take the trend in TXTW correlation that we have observed and apply them to model projections of global warming and see how it changes the projection of TXTW trends in the future. So what we have is that we're going to represent the trend in or the change in the TXTW correlation as two components. So first is the change in the TXTW correlation per degree Celsius, and then this sort of rate of change per degree is multiplied by the change in temperature. So the first term, that change in TXTW correlation per degree C, we're going to estimate from ERA 5. And then that second term, the change in temperature, we're going to estimate from CMIP6. And so this is going to give us a sort of correction of the TXTW change in the future using the observed sort of relationship between the TXTW correlation and temperature in the historical period. Now, of course, there could be reasons why this relationship between the TXTW correlation and temperature changes in the future. And that is definitely possible, but we're going to do this and sort of get a sense of how different our projections of TXTW correlation might be if we take this sort of observed rate of change from the recent past. Okay, so when we do this, the results we get look like this. So on the y-axis, we have the projected change in the TXTW correlation relative to the historical period of 1981 to 2010. And this is again under the emission scenario of SSP 245. So this is that sort of mid-range 2 to 2.5 C warming scenario. So the black line here is just the CMIP6 projection in the TXTW correlation. So we just pull this out of the CMIP6 models, and this is showing the multi-model mean projection going forward. So this is just the straight CMIP6 data. The red line shows the projected TXTW correlation using that ERA 5 based rate of change per degree C. So that change in TXTW correlation per degree C over the historical period, and then applied to the temperature change projected by CMIP6 models. And so what we see is that using that ERA 5 based rate of change, we get a substantially larger decline in the TXTW correlation than we get if we just ask the CMIP6 models directly, how will this correlation change? And the difference is quite large. It's, say, almost a 50% increase in the decline in this correlation using that ERA 5 based relationship. So to summarize here, we started off by sort of noting this recent result, finding that CMIP6 models tend to be too humid. And what we found here is that CMIP6 models tend to underrepresent the decline in the TXTW correlation in the historical period. And if you sort of correct for that underrepresentation of the decline going forward, we end up with a projection suggesting that the correlation between temperature and wet bulb temperature will decline by substantially more than is represented in the models. And this is consistent with that original result saying that the models are too humid, right? Here, we're basically saying that the hottest days of the year appear to be getting drier at a faster rate than is represented in models. And so the wet bulb temperature on those hot days is either going down more or increasing less than the models say. And so overall, we could characterize this result as saying that it seems that heat or sort of dry and humid heat days are becoming more distinct and either occurring at different times or just the hot days of the year are getting less humid and the humid days of the year are getting a little bit less hot. Okay, so I will stop there, and I'm happy to take any questions.